Good morning. I'm going to briefly talk about electron configurations and orbital diagrams. These are basically addresses for where electrons exist in the orbitals that the quantum mechanical theory kind of came up with, Schrodinger and his gang. So have your periodic table out because you're going to need it a lot. And then please take notes on this because you'll want this to refer back to whenever you're doing your problem sets. All right, so your first question is, how are electrons arranged around the nucleus? We know that Schrodinger and his gang and the quantum mechanical theory said that they were in orbitals. Well, we had different types of orbitals. We had s orbitals, which were spheres, p orbitals, which were dumbbell shaped, d orbitals, which were double dumbbell shaped, and f orbitals, which were kind of flower crazy looking orbitals. So we have to specify which of those orbitals the electrons are in whenever we're talking about the electron configurations or where the electrons exist in the atom. There are some rules on how we can write out these electron configurations. It's like a code. It's a long address that tells you where the electrons are. So these are the rules for the electron configurations. First one is called the off-ball principle. The electrons enter the lowest energy level first. So when we said n is equal to 1, that was also the principal quantum number. I'm just going to put Q number. And then we also said it was kind of like the period number. And so the kind of like period number is what we're going to be referencing a lot today. So we always start from 1 and then go up to, n is equal to 7. Don't start like 7 and then go to 4 and then 5. So it's just, that's pretty logical. The Pauli exclusion principle is the next one. And I always remember it like this: Pauli pair. That means that you can't have more than 2 electrons in any one orbital because electrons repel each other, so they like to be as far away from each other as possible, and we don't want them right up on one another. And if we have to, we have to, but if we have the choice not to, that's what we prefer. And that's where Hund's rule comes in. Hund's rule is how I remember this. And it's that one electron is going to be put into an orbital before we start to pair them up. And that's going to limit the amount of repulsion that we feel in the atom and the instability, which helps whenever we're talking about reactivity. All right, so whenever we write out electron configurations, we always write it out in this format right here. Sorry, my penmanship is great here. The first big number is the energy level, and it's also the period number. Oops. And it's most likely it's going to be the period number, so I'll tell you one exception here. That's just going to tell us the first principal quantum number and where about we are on the periodic table and what atoms we're talking about, what elements we're talking about. The S here is representing the type of orbital. Remember, you can have S, P, D, or F. And this little exponent up here tells you the number of electrons in an orbital or in that sublevel. A sublevel is S, P, D, or F. So we're going to specify the number of orbitals within each of these sublevels as well. So this terminology is really important. Just listen to me as I go. But the sublevels are these shapes in the orbital. We usually represent as just one single space like this. And I'll tell you how we add our electrons in this little space in just a minute. So if you're looking down here at these other examples, oops, let me go to big screen here. If you're looking down here at these other examples, you've got 1s2, which means we're in the first energy level, s spherical shaped orbital, and there's 2 electrons within that certain sublevel. The 2 means we're in the second energy level. The p means we're in this orbital, like this. There's one that goes up and down, there's one that goes side and side, and there's one that comes out of the board and then into the board. So there's the 3 orbitals from the p. Each of these orbitals hold 2 electrons each, which is how we get a total of 6 electrons. That's how we get the 6 up here, telling you the total number of electrons in that subshell. Last one is the 4th energy level. We're in the D-shaped orbital, and there are 10 electrons here. So these are important ones because these are actually the maximum electrons that can exist there, and I'm going to show you on a picture why. Well, first let me tell you about the periodic table. The way this works is the electron configurations correlate directly with where this atom exists on the PTOE, on the periodic table. So everything in these first two groups are called S block. This is where you're going to probably be labeling this on your periodic table. Everything in the first two groups are S block. And then notice that this little helium over here actually does belong in S block. So I'm going to put helium right here. Because it's so tiny, it actually is going to be one of the simplest elements, and so it needs to only have simple orbitals, which are the s orbitals. Then we jump over here to the third group, to the eighth group. And these are called p block. Everything here has a p in it. And these are going to be the more complex orbitals. Notice that there are 3 times as many groups. So we've got group 3 and 4. Group 5 and 6, and then group 7 and 8. S block can only hold, an s orbital can only hold 2 electrons each. P's can hold 6 electrons in total. Then we go to the middle section, the transition metals. The T metals are all making up D block. D block. And they are here in the middle, and these are the B groups. And there's one special case here. You'll notice that the 4th energy level, when we jump into D block, it drops down to the 3rd energy level. So we have the special rule here called N-1. The last one is called F block, and that's the lanthanide and actinide series. And that's because right here on the periodic table is lanthanum and actinium. And these 2 groups actually insert right into those spaces. Notice the periodic table, the numbers correlate as well. Lanthanide is number 57, so if you look up there on the periodic table, it's number 57. And then the first one here on the F block is 58. So it's according to the atomic number where they insert. And then you've got the actinium, which is number 89. And then the first one here on the periodic table is number 90. So these insert here, which means that they actually have a similar principal quantum number, but not exactly. So see here we have 6s. Whenever these F blocks insert, they have a special rule as well. It's N-2. Then we jump back into the normal flow things, which is D block, and that's where we have 5D because of the whole N-1 rule. These down here in D and F block are a little bit more difficult, but I'll walk you through a couple of examples. All right, so on our periodic table, if I wanted you to write out the electron configuration of, let's say, hydrogen, simple. You are in the first energy level, so you write a 1 because you're in the first period, and you're in S block, so you write S. And then this is only 1 electron over, so the first electron will be here and the second electron will be here according to the group that we are in. So 1s1. That is the electron configuration for hydrogen. And hydrogen only has 1 electron, so it's really easy. The 1 electron is represented right there by that 1 exponent. Lithium is another period down. So we have to account for all the electrons that exist in helium, which lithium has 3 electrons. And we have to show how they are arranged, and from period to period and from sublevel to sublevel. So lithium has 1s, because we have to travel through the hydrogen and this helium, which actually exists over here, but I'll draw it right here for you. 1s, and then there's 1 electron, 2 electrons. So that's called 1s2 to account for both there. Lithium's in the next period, so we put a 2 here. We're still in S block, so we put an S, and it's 1 electron over. So total electron configuration is 1s2, 2s1, and that's a total of 3 electrons. Good, that's what lithium has, so we needed to account for all of them. Take a minute and try to do potassium. I'm going to pause the video for just a second so you can try that. All right, if you took a second to try potassium, you should have realized that you have to run through many more groups. So I'm going to start here with hydrogen, and we're going to pretend helium is here as well. So when you travel through the periodic table, you have to account for every electron until you get to your desired atom or element, which is way down here, potassium. So you should go 1s2, which is accounting for these 2 electrons in the very first energy level. Then you drop down. We're in the second energy level with where lithium is. We're in S block, and then we're accounting for the 2 electrons that make up S block. So that's 2s2. And then you have to go all the way across to P block, which is where we're first going to start introducing the P's. So we're still in the second energy level, but now we're in P, and we're going to go through all 6 of these elements so we can finally get down to sodium. So it feels like you're traveling across the rows. So that will be 2p6 because you saw 1, 2, 3, 4, 5, 6 atoms. The next one is dropping down to sodium magnesium's area. Sodium and the magnesium are in the 3rd period in S block, so 3s, and then we're 2 electrons over, so 1, 2. Then you've got to go all the way across to Cp again. And this is representing the 3p level. So there's 3 because we're in the 3rd period, p because we're in P block, and then we've got 6 electrons that we are traveling, 6 atoms, elements that we're traveling through. So that's going to represent 6 electrons. So far we've got 1s2, 2s2, 2p6, 3s2, 3p6. Now we're finally to potassium, and we're going to stop there. But we need to write down that last electron we're accounting for, which is in the 4th period. It's in S block, and there's 1 electron there. So if you go through and count up, 2 plus 2 plus 6, that's 10. Plus 2 is 12. Plus 6 is 18. Plus 1 is 19 electrons. 19 electrons directly relates to potassium because it's atomic number 19. So it has 19 protons and 19 electrons because it's neutral. So that should be the same as the total number of the exponents of your electron configuration. Okay, so try a couple of these. We've got some examples here now. So oxygen is pretty easy. You should have your periodic table out in front of you. You'll notice that we have to travel through 1s. We go through 2s. So that's 2 electrons there, 2 electrons there. And it stops midway in the P block. So when you're looking at oxygen, 1, 2, 3, 4, 5, 6, oxygen's right here. So we're accounting for the first 4 electrons, which is why we have a 4 here. And then you can verify that this is oxygen because oxygen has 8 electrons, therefore 2 plus 2 plus 4 is 8. How do you represent these electron configurations in orbital diagrams? So these are the pictures that you'll be drawing that directly relate to the electron configurations. It's actually really easy. I always write the electron configuration first, and I put a line here to represent each orbital. So this is going to be the 1s orbital. Each orbital holds 2 electrons, 1 up, 1 down. I draw these as little half arrows because I'm lazy, but there we go. Those are actually what the arrows look like. So these are the 2 electrons directly that we've written right here. We have to put them in opposite spin because they repel each other. And if we put them in opposite spin, then that means that they're going to repel each other less, and it's going to make the atom more stable. The 2s is the next one we're going to do. So we put a line, we put 2s, and there's 2 electrons in this orbital according to the electron configuration. Then we have the 2p. Now 2p has the ability to form 1, 2, 3 orbitals. So I put a line here, 3 lines here, and then I'm going to put 2p down here to represent this. All represent 2p. And then this is where we use Hund's rule, where we go through and we put 1 electron in each of the orbitals first, and then we have to go back and pair up. So we have 4 electrons to work with. We put 1, 2, 3 in there, and then we had to go put the 4th one back in the very first one. So I know that you will do this correctly, because if you don't, you're going to do something like this. You're going to put your 3 orbitals, and you're going to go 1, 2, 1, 2. I know that this does not look like this. Therefore, I know that you did not follow Hund's rule. So that's wrong. This is right. You have to go 1 in each one and then go fill the first one back in. And that's just following the rules of the electron configurations. You can see a couple more examples of this. So like oxygen is one that we just kind of did. So we've got the 1s2, 2s2, and then the 2p's right here. Fluorine is similar, but it's got 1 more electron. So we've got 1s2, 2s2, and then here's our P block. We've gone 1, 1, 1, and then refill 1, 1 here. So that's a total of 5 electrons in the 2p. So take a minute and look at these, but these are orbital diagrams. They're just drawing the orbitals out with the pictures going along with the electron configurations. All right, let's try some of the more difficult ones. Let's go to chromium. Chromium is one that's going to be existing in D block. So find it on your periodic table. It's atomic number 24. So if you're looking midway through D block right now. So when you start writing it, you're going to start from the top again, 1s2, 2s2. You're traveling through your periodic table with me. Okay? Then we're going to go down to 2p6, so we're traveling all the way through the P block. Then we're at the third energy level, so 3s2. So we pass through sodium and magnesium. Then jump all the way across and where you see aluminum, so that's 3p6, all the way through aluminum through argon. Then we're finally back at potassium. We really just did that first sequence again. But potassium and calcium are on the fourth energy level, S block, and they make up 2 electrons there. Then we enter D block, and this is where you do the N-1. So D block is going to be 3, not 4, 3D. And then count how many over chromium is. 1, 2, 3, 4. 3D4. So that's it for chromium. How do you double check? You count your electrons. 2 plus 2 plus 6 is 10. 2 plus 6 plus 2 is another 10. So we're 20, and that's 24. So that's 24 electrons. Yay, that's what we wanted. Let's do another one. Strontium is, well, it's a bit lower. We'll do strontium. This is with the SR. So this is the same as we just did. Strontium is right below calcium. It's number 38. It's in the second group. So we've got 1s2, 2s2, 2p6 again, all the way through those, and then we'll go through the third energy level, 3s2, 3p6, and then now we're down our fourth energy level, 4s2. This is where we do our whole jump down the energy level for a second, 3d10. You'll notice there are 10 electrons all the way across that D block. Then we're back in P block. When we get back to P block, we have to go back up to our original energy level. So we're going back to 4. So we went from 4s to 3d to 4p. We're going through all the way through P block, so there are 6 electrons that exist there. We're finally down close to strontium, and that's 5s2 to represent it all the way over to there. That should be 38 electrons. Last one I'll do is tungsten for now, and that's because it's involving the F block, and I want to give you some examples of this one. Tungsten is going to be the same sequence all the way through that we just did until we get down to the 5s, then we have to go to 4D. So I'm going to write the first bit a little bit faster, but go ahead and take your time and pause the video if you need to. 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, then we're right here at 4s2, but at calcium, 3d10 again, back up to 4p6. Now we're in the fifth energy level, 5s2. Now we're at strontium, so that's where we just previously were. And we're at the Y, which is yttrium. That's going to be 4d10 all the way across. Then we're back into the 5p6. So now we're all the way to xenon. Now we're going to drop down to the sixth energy level, which is cesium. So 6s2, which is cesium and barium. This is where we insert our F block right now. So lanthanum is, yes, I know it's number 57 and it's before 58, but if we insert this now, it'll make our life a little bit easier. So F block includes N-2, which would be 4F, and then count those electrons all the way across F block. There should be 14 elements. So once you've gone through the first level of F block, go back up to D, which is where lanthanum is, number 57. Once you go back up to D block, you have to go back to the 5, which is N-1. 5D, this is where you tell me how many electrons over tungsten is. Counting 1, 2, 3, 4. So lanthanum, hafnium, Ta, and then W. W is tungsten. 4 electrons over. Whew, that was a large one. If you counted up these electrons, it should be 74 electrons. Uranium is also a large one. It's number 92. So if you want to practice another one of those, uranium actually stops in F block. So that would be an interesting one to try. All right, the couple of exceptions to electron configurations are the ones that relate to ions. Ions are different than their normal elements because they've got a charge. That means they've either lost or gained electrons. So looking at magnesium, it has lost 2 electrons. That's how it got this positive charge. So I'm going to show you how we look at the periodic table to tell where we go with this. So I'm going to jump back a couple of spaces. Let's go here. Okay, magnesium, which is here, once it's lost 2 electrons, it's no longer at this specific electron configuration. It's gone back 1 space and then all the way back to the last noble gas it just passed, neon. So Mg2+ has an electron configuration the same as neon. So we're going to write out the electron configuration for neon, and that will also represent magnesium. So when you're looking at your periodic table, you go 1s2, 2s2, and then look where neon is. Neon is the 6th one over, so that's 2p6. That has a total of 10 electrons, and that makes sense because magnesium originally had 12 electrons, and once it lost those 2, it's now at 10 electrons. So you can double check your math that way. Let's do nitrogen. Nitrogen has a 3- charge. So that means it's got more electrons than what it started with, so it gained 3 electrons. How do we see that on the periodic table? Right here. Here's nitrogen. Nitrogen gaining 3 electrons means it goes up 1, 2, 3. Guess what? It's also having the exact noble gas configuration of neon. So I'm adding it to my little box here. That means that when we write our electron configurations, you have to specify sometimes or think about if you're talking about an ion or the actual element. So that's why I chose these 2 examples, because it's really weird, but they have exactly the same electron configuration because the electrons have been removed or added. These other ones, you can go back. This one has lost 1 electron. Copper 2 has lost 2 electrons. And I will do this one because this is a transition metal and you don't know where the electrons are lost from. So let's go find copper. It's in D block. All right, here is copper right here. Copper can either lose electrons from where it is here, or it can lose electrons from its outer valence shell. So let's write the configuration for this first. All right, so when you look back at copper, you'll realize that it's going to have some variability in the electrons that it loses. So let's write out its configuration first. I'm going to write it right here. 1s2, 2s2, 2p6. So now we're all the way through the second energy level or second period. 3s2, 3p6. We're all the way through the third period. 4s2. And then this is where we're going to enter D block again. So we have to drop down 1 energy level. So 3d. 1, 2, 3, 4, 5, 6, 7, 8, 9. Therefore, copper is the 9th one over. Now, when it loses 2 electrons, the reason why it doesn't lose anything, it's not losing it from this D block, it is losing it from S block, is because the 4th energy level is the valence shell of electrons. And so the valence shell are the ones that get lost whenever you, or gained whenever you are changing around electrons for ions forming. So these 2 electrons from 4s are the ones that's going away so that you can lose those 2 electrons so that it can get that 2+ charge. So I think you should write out the electron configuration first and then decide which ones are lost. So the new one is going to be 1s2, 2s2, 2p6, 3s2, 3p6, 3d, oops, scratch that out, 3d9. All right, let's do one more orbital diagram. This is going to be one of the more complex ones because you need to understand how to get to D block and how to write the electron configurations in the orbital diagrams for that. So let's do zinc because zinc is one that's going to be in D block. So write out your electron configuration first, 1s2, 2s2, 2p6, 3s2. My goodness, this is taking us forever, right? Sometimes they are a little lengthy, so I'll show you a shortcut in just a second. 3p6. 4s2, then we drop down to 3d. Count over all the way on zinc. Zinc's the farthest one on the right, so that's 3d10. So let's correlate this to our orbital diagrams one more time. 1s, 2 electrons. 2s, 2 electrons. 2p, 1, 2, 3 orbitals. Draw yourself a little bracket to say all these are 2p. And then 1, 1, 1, 2, 2, 2. So there's a total of 6 electrons there. 3s, 2 electrons. 3p, for 3 orbitals. Designate them all as 3p. 1, 1, 1, 2, 2, 2. And then let's do our 4s. And then 3d, we're going to need 5 spaces. So S's always have 1 orbital. P's always have 3 orbitals. D's always have 5 orbitals. F's always have 7 orbitals. It goes up by 2 each time. So here's our 3D. 1, 2, 3, 4, 5. Label it all as 3D. And you go 1, 1, 1, 1, 1. And then 2, 2, 2, 2, 2. So all of these are fully filled. So I probably won't know if you fill it in according to what Hund's one rule or not. But it's good practice so that when you don't have it fully filled, that you won't make the mistake. How many electrons should be here? We should have 30 electrons total here, and you can count them if you want to. All right, the reason I wanted to show you the copper one, because whenever we're talking about the valence electrons, sometimes they get kind of iffy. So this little diagram is called the off-ball diagram. Oops, off-ball diagram. And this is the 4s and 3d level that are so entirely close together. I always tell you to lose the fourth energy level electrons, because these are really, really close together in terms of their energy. 3d is a little bit more energetic. However, that 3 right there means it's embedded deeper within the atom. So we always lose the 4s there, or the same thing with like 5s and 4d. Usually we'll lose those 5s. And so on. So the energy levels are far apart from each other down here, from 1s to 2s and so on, and they get closer to each other as you go up in number. That would be a good multiple choice question to know. All right, these are for you to try. You need to try as many as you need to get comfortable with this. there are some on your problem set as well, so I'm leaving you up to choose how many you want to do here. Last thing is let me skip this one for a second. Last thing is, how do we excite electrons? We excite it by either adding heat, fire, or electricity, which we will do in our flame test lab whenever we do our flame test lab. And so an electron is going to get excited. It goes from its normal stable ground state to its excited state, which is where it is very unstable. Since the electron is unstable in this excited state, it falls back down, and that's when we saw the Bohr model, we would see light with that. We would see some color with that. So if I wanted you to, I could set up the whole scenario where we're jumping up to another energy level, and it falls back down. You see, yellow light, red light, whatever. You could calculate the wavelength, frequency, and energy from that using your formulas. Or I could ask you to write an electron configuration for that. So normally calcium is 1s2, 2s2, 2p6. Look on your periodic table with me. We're all the way down to 3. So 3s2, 3p6, and then all the way through 4s2. So this is normal. This is ground state. If I wanted you to show me the excited state, one of these would be jumping to an unfilled orbital. So I like to just choose the last one and make it jump. So we're going to cause one of these 4s2s to go up. Oops, drawing orbital diagram. We can go 4s1, 3d1. So I took one of these electrons, left it where it was, and then pulled the next one to the next orbital, which in this case is the 3d. So all of it's the same, 1s2, 2s2, 2p6, 3s2, 3p6, and at the very end, we're going to put 4s1, 3d1. So that's just an example of one. It's making it excited. All right, here's the shortcut I wanted to tell you about. So yes, you have to know how to write the longhand version of this, but if I want you to, or if I want you to use your time wisely, I'll allow you to write the shortcut version. So the shortcut version is going back to the previous noble gas you passed through when you're looking through your periodic table and you're going line by line by line. And then you can put a bracket around that noble gas. That bracket means that I'm going to represent everything, all those electrons before the noble gas. And then you have to finalize it by writing the rest of it. So notice that we stop at 3d10 again. If you look on your periodic table at 3d10, that one is zinc. So earlier for zinc, we had written all those energies right, here. We'd written all these electron configurations, 1s2 all the way through 3p6. If you look at this on your periodic table through 3p6, you'll notice that this is argon. So we put a bracket around the electron configuration of the last noble gas, and then we complete the rest of the electron configuration to finalize the atom or element we're looking for. So that's why you see argon, 4s2, and then 3d10 right here. So this one right here, argon in brackets, and then 4s2, if you look at your periodic table at 4s2, you'll notice that it's calcium. So these are shortcuts for how to write electron configuration. So we'll do one example real fast. What if I want you to do barium? Barium is way down in the 6th group. Barium, take your barium and go back to the last noble gas. You'll notice the last noble gas that it just passed through was xenon. So we write bracket xenon, and then we go forward. From xenon forward, we go right back to cesium and barium, which is 6s2. This is way shorter than writing all the electron configuration stuff before. All right, so 30-minute video. Hopefully you've learned something, and I need you to go through your problem set 4 and ask me questions. You can email me anything, but please go ahead and watch this video again if you need to, or certain parts of it. Good luck, and see you soon.